Hey everybody, and welcome back to Calc 3 Online. So I just want to go through a few problems today that are kind of like the ones in the Chapter 14 quiz here, and let's just get into it. So the first kind of thing that we looked at was how to analyze functions of multiple inputs. So if I asked you to describe algebraically and geometrically the domain of the following function, I would basically just, there's no issues with the inputs here, but down here you need this part, 9 minus x squared minus y squared minus z squared, to be greater than 0. And so if you kind of reorder that, right, you get x squared plus y squared plus z squared needs to be less than 9. And that's a sphere, right? That's like an open sphere. So it's kind of like if you, I don't know how I'm going to draw this. That's a good circle. I'm proud of myself. But basically it's like if you, have some sort of sphere. Maybe I'll try and use colors to make it a little more clear. But basically there's like a ball centered at the origin. It goes out to 3 and back to -3 and all the axes, right? But anything in that 3D open sphere is what you could basically plug into this function. It's going to plot into 4D, like 4 spatial dimensions, but yeah, it's just an open sphere. That's what the domain is geometrically, and algebraically you just write it like that. And then this last question, so can the range of this function be negative? And so the only way this thing can be negative, because assuming real valued function, this is greater than or equal, well, it can't be 0 because it's on the bottom, but this is greater than 0. And this in here is the only place where you could get a negative, like the top. So basically you would need 3x minus 4y plus 2z to be less than 0. And if you just kind of think through it a little bit, you could kill this term and this term with a 0, right? And then you just need there's lots of y values in here where this could be less than 0. So, you could take y to be, I was about to write a 1 and then I kind of messed it up. But you could do 0, 1, 0, right? And that's a place where the function could be negative. So yes, it can happen. Yeah. So another important thing that we did is do these implicit derivative problems. So I just want to do another one of these. I actually think they're honestly kind of the same thing. Let's just do, instead of both of these, let's just do partial z with respect to y. So this function is, it's just got the, you're not going to need to do a product rule because you just have this one function of y. So you would just literally get, if you take the derivative with respect to y, you're going to get e to x squared e to the y. But then over here, you have a yz function, let's say, and then I don't want the yz one. Let's just do, let's think of it as y e to the x. No, I don't know why I'm doing that. Let's do y and then z e to the x. That's a good one. So this is you're going to have a bunch of stuff going on here because you're going to have chain rule with the implicit derivative part when it comes to z. And then you're going to have a product rule because z is a function of y and x. And so this is a function of y and this is a function of y clearly. So you got a lot of stuff going on here. So I'm going to just do this to kind of not have to deal with that negative right off the bat. So the derivative of y with respect to y is just 1. So then we get z e to the x because you multiply by the second function with the product rule. And then you add to that the derivative of the second function, which is just the partial of z with respect to y, and then e to the x. And then you have to multiply by the first function, which is y. And then, the derivative of 0 is 0. So now I can go and, distribute stuff, isolate the partial, and then be done. So we got x squared e to the y minus z e to the x minus partial z with respect to y e to the xy. I'll probably just move the partial over to the right. And then divide by e to the xy. So then the partial of, the final thing here, the partial of z with respect to y is just x squared e to the y minus z e to the x over e to the xy. All right. Another really important thing that we've been talking about are these limit problems. And this is one of those where you can actually show this does not exist. And the reason I can see that is, so I've got these two squared terms in the bottom, but I got two different variables that are not squared here. So if I come in on like diagonal lines, like y equals x or y equals negative x, I should be able to introduce a negative somewhere that's going to throw things off. That's kind of how I look at this and think about it. So I'm going to try to come in first on y equals like x and see what I get. So I would do limit as xy, I want limit as xx approaches 0, 0. And then I'll have 3x squared up here. And then 3x squared, and then all the y's are just becoming x's, right? So then, I guess I'll write it down here. All right, so then, just combine like terms there, cancel this off, and you can get 3/4, right? I just realized somehow I just randomly wrote a 3 instead of a 2. So let's change that. So this should be 2x squared, 2/4, or 1/2. There we go. So now I just need to try to think of a different path where I can get like maybe a different number to show that this thing actually doesn't exist. And you actually could do like a lot of options. Another one I'm actually seeing right now is if I come in on the let's say the x-axis. The x-axis is where you just have y equals 0. Then you would have this limit problem. So instead of xy, you're going to have x0 approaching 0, 0. And then you've got 2 times now 0 up top, times x, but I guess I should put that in. Then you have 3x squared, plus 0. And so the 0 on top is basically going to take over, and so you're going to be able to just say that then equals 0. And so since 0 doesn't equal half, right? This limit doesn't exist. We just showed that along two different paths. Y equals x, and the x-axis, y equals 0. We get two different things, and so basically that means that as we come in the same point, we got some sort of jump discontinuity kind of thing. Just kind of like when Calc BC and stuff, we get those problems where it's like this, and the limit, at this point right here doesn't exist because it's defined up here, but then it jumps down, and it looks like it's lower when you come in from the left. So it's basically just the analog of this idea. All right. Another thing we've done lately are these tangent plane problems, and just thought it'd be good to do another one of these. And basically what you're just doing in these problems is you have like some sort of surface. I'll just kind of always draw this one. And you've got like these paths. Let's say, this is the x direction and this is like the y direction. And you got like a point there. And so if you take like f with respect to x, and then you take like f with respect to y, the partials in those directions, they can kind of dictate the slope of the tangent plane in the two directions at the point. And then you can plug those into like a linear planar equation. And as long as you put them in the right spots, you would have an equation of the tangent plane. So we first need the partials. And so if you take the partial of this thing with respect to x, you're going to get 4x minus 3y plus 2. And then if you do it with respect to y, you're going to get minus 3x plus 16y minus 4. And if you plug in, you need like the slopes, right? So if you do this at the point, you would get 13. And if you plug this one, that's an at symbol, at the point, you'll get negative 26. So now I have like my, this is like my M1 and my M2 that are going to go in that equation. And so I just kind of take this general linear equation. Right? The, x naught, y naught, z naught are just the point, and then the M1 and M2 we've got now. And the only thing we basically need, we have this, we have this, we have this and this. We just need to know what the z value is at this point. So you have to go and do like f of 2, negative 1. And I just did it out before, but it's just plug and chug. If you do that out, you should get 34. And so if you've got that, this is my z naught now. I can just go and I can plug in everything. So 34, I've got the 13, let's say, for the x one there. And then we've got 2 and then negative 26. And then, what's my y point? Negative 1. So z minus this equals 13 times x minus 2 minus 26 times y minus 1. And that would be it. This would be an equation of the tangent plane. And you could like simplify this thing down and get it into like a more like normal, like ax plus by plus cz equals like a number form. I don't really care about that, but the idea is what's more important here. All right. One of the things that's probably the most important that we've learned so far is just literally how to take big, messy partials. And we've got here a pretty big, messy looking thing. It's a 3-input, 4-dimensional function, some sort of hypersurface thing. And I want to know the third order mixed partial with respect to x, y, z. Okay? And one of the most important results that you saw with the higher order partials was that the mixed partials are all equal. So it doesn't matter if we do like f with respect to, I'll write these out. So like f x, y, z is equal to f, y, x, z, which is equal to f, which ones am I missing? Y, zx, there's a whole bunch, I guess. I think there's 8 of these things. So there's a bunch of those, but it doesn't matter the order in which you do them, right? You can just do them in any order. So when I see a function like this, specifically this part over here, I always see that, if I got all this z stuff, I would have to do like a triple product rule thing. It'd be a whole mess if I did it with respect to z first, but you just should not do that, and then it'll work out nice. This would all go to 0 if you do it with any of the partial y or partial of x first. So what I'm going to do is I'm basically going to do partial, I'm going to do z last, and then take that of, like, let's just say y, and take that of x. So I'm going to start off, boom, okay, I got them all there. I'm going to start off and do my partial of f with respect to x. So if I do that over here, right, this whole thing now gets killed because it was all in terms of z, which is nice. So then I would just get 3x squared, and then the rest of this stuff is just constant. And then f with respect to x, y, so doing y next, you can just copy over the 3x squared, and then you're going to have 2y, right? And then z to the fourth, which would simplify to 6x squared y z to the fourth. Then one more, x, y, z, is going to be, you just do, bring a 4 down in front and drop the power on the z by 1. So you're going to get 24 x squared y z cubed. And that is it. And that is definitely the best order to do it in. I mean, to be honest, it doesn't matter if you do y then x or x then y, but don't do z first, because this would be really annoying. And no matter what, that'll eventually go to 0, even if you did z first. But the order, you're going to save yourself tons of work. I mean, this is all the work you need to do if you don't do z first. If you think about taking the derivative of that, it's really annoying.